Thank you very much. So I'll use this mic because apparently I'm supposed to. So before I begin, let me first extend an acknowledgement to my student, Rahmani, who is the chief architect of what I'm going to be talking today about. So he gets all the credit for all the good things that we have to say, and I get all the blame for all the negative things that end up being caught. But anyway, so this is very much his work. So today I'm going to talk about some ideas that we've been exploring over the past few years, broadly in the context of trying to understand scalable distributed systems and how we might go about testing them in more meaningful and precise ways. So the setup for our problem is actually quite simple. We're looking at a collection of transactions. So we're looking at database programs. These database programs are comprised of transactions that execute concurrently in some form, and they manipulate a database of some kind. So the context or the structure of these transactional programs, think of them as SQL programs, very much along the lines of what we heard about in the last in the keynote this morning. So we've got highly structured data. Clients invoke these transactions. We've got some mechanism for manipulating them. And the question that we want to ask is, what do these database programs mean? Now, in fact, as many of you know, there's already a well-understood methodology and a well-understood set of reasoning principles for database systems that have been explored over many, many decades. And that's euphemistically referred to as the sort of asset guarantees that we expect database transactions to provide. That is, we are going to simplify the reasoning methodology that we employ for thinking about database programs, these highly concurrent database programs, by imposing some structure, additional structure on what these transactions can see and how they can affect other transactions. So these asset guarantees stand for a collection of properties that we expect transactions or implementations of systems that these transactions are executed on to preserve. So the first property is atomicity. So that simply means that if I have a collection of updates performed by a transaction, it will appear as though all of these updates happen instantaneously to the database, right? So we don't see intermediate effects of transactions. Transactions don't see intermediate effects of other transactions as they execute. The second property is consistency. So we assume that all transactions get to see a sensible view of the database as they execute. So one very simple notion of consistency is everybody sees the exact same copy of the database, right? So that's a useful property. And the third property is isolation, which says that transactions should not interfere with other transactions. So as a transaction is running, it should not see the effect of other committed transactions until it itself commits. So this sort of, in some sense, linearizes or sequentializes the behavior of transactions in some sense. And the final property that we want to support is durability, and that basically says that every committed transaction, the updates of every committed transaction should actually be stored persistently. So these are all very, very nice properties, and the first three in particular lead to what's known as serializable transactions. And serializability, as the name implies, means that we can think, despite the fact that there's all sorts of concurrency going on, we can, for the purposes of reasoning about programs, imagine that these transactions are executing in some serial order. So that's all very, very good, and it leads to a very simple model of the world. So here's a simple example of a database program. It selects some fields or some rows from a table. It performs some updates to those rows, and even though we have two transactions and they may logically execute concurrently, it will appear as though they are going to execute in some serial order. So as these transactions select rows and then update fields in these rows, it will appear as though each of these selects and updates happen in some sequential order, which is all very good, and it gives us a model in which we can think of, for example, in this really, really simple example, the number of transactions being in some sense related to the final value of a particular field. So serializability is all well and good, but if we want to actually realize it in practice, we have to impose certain constraints on implementations, and these constraints are actually expensive. They're not cheap, and so most databases which want to impose serializability, which want to provide serializability, must do so using significant synchronization and other sort of heavyweight mechanisms to allow programmers the flexibility or the luxury of thinking in this very simplistic and elegant world. But as we scale up, as we wish to scale up, these costs become prohibitive. And so we essentially have to discount them and try looking at something else. And so we come up with a dichotomy. We want to be able to think simply, serializability gives us that, but we want to be able to get efficiency, and implementations will not admit serializability in pursuit of efficiency and scalability. So what actually happens is real implementations in practice will in fact break pleasant properties like isolation in pursuit of scalability and efficiency. And so now all of a sudden, this very, very elegant model that we've come up with no longer applies in practice. We actually have transactions that may in fact witness the behavior of other transactions or the effects of other transactions as they execute. So once we break serializability, all sorts of weird things can happen, right? So for example, that simple example that we talked about, we just showed, where we can sort of relate the updates that are happening in a transaction with the final value of a particular field, now all of a sudden that doesn't apply. That sort of reasoning mechanism doesn't apply. These transactions can now start executing concurrently. They can start witnessing the value of fields as other transactions are updating them. And so the sort of interleavings that are admitted now look very similar to racy interleavings that you might see in a shared memory concurrent system, and that's all bad. And we know that races are bad, and we work very, very hard at trying to avoid them. But in this database universe and in this sort of scalable distributed universe, that's actually what people want, or at least that's what implementations provide, and we need to do something to avoid it. Observe that from the programmer's perspective, they have no control over how the underlying database engine is going to interleave these actions. They just say, here's a transaction. And their expectation from their worldview or from their mental model is to simply have these transactions execute serially, but the implementations are going to do something very, very different. Okay, so bad things happen, right? So that's the upshot. And the problem becomes even more exacerbated as we look at things at scale. So when we actually look at sort of geo-replicated systems, we look at systems that are going to actually replicate the database across multiple nodes, that are going to then be loosely synchronized at best. We find that all of these problems manifest in many, many different ways that we can't necessarily imagine upfront. So this particular problem that I've set up isn't an academic problem. In fact, almost all major databases admit weak isolation and admit these kinds of weak behaviors. And indeed, in an interesting study by Bayless and his colleagues a few years ago, they actually looked at 18 different real-world databases and found that very few of them actually support serializability as a default. And amazingly, a non-trivial number of them don't even support serializability at all. Even if you insisted on having serializability, a number of these databases simply say, we're not going to give it to you. So if you try to program transactional systems on those databases, you're going to have to figure out a different solution. You simply are not going to be able to rely on what we've learned in our classes about the way we should program these kinds of systems. So we've got an issue. We have a problem. Okay. So one way we might go about doing it is to say, well, okay, let me program thinking that my applications are in fact going to be serializable, and let me see if the behaviors that are induced by the underlying system break interesting invariants, break the properties that I want. So I can write a database program, I can have some invariants, and now I can ask, if I executed this database program under weak behavior, will these invariants get violated? And so the question that we want to now find out is, can I actually discover, can I actually explore the space of possible executions in a meaningful way to discover whether these invariants would actually get violated? And if so, how can I sort of reproduce them? How can I actually provide information useful to the programmer so they can try to fix their programs at least? So the problem is that these database programs are non-trivial, right? There's a whole bunch of things that we need to get right in order to be able to trigger these kinds of anomalies. So for example, we might need to think about the initial state of the database, because maybe for certain values we don't get a violation. It only gets triggered when there's a relationship, say, between different fields or different rows in the database, and we need to sort of discover that in order to be able to start execution in a way that sort of causes the problem to be manifested. We might have to figure out what arguments we want to provide to different transactions. we may need to figure out interleavings. Now, all of a sudden, the minute that we start thinking about interleavings, we've got this large exponential state space of possibilities that we have to consider. And we need to think about, because we're running in this sort of geo-replicated world, we need to understand what the possible effects of network delays and partitions, node failures, other such things that happen in practice, what those effects are with respect to the actual behavior of the programs that we want to validate. Okay, so this is a big problem, right? Now, there's two ways that we can think about doing it, at least two ways we can think about doing it. One way of considering how to address this question is sort of to give up and say we're not going to look at the code itself, we'll just look at executions, and we'll try to see whether we can somehow jigger an execution to sort of lead to a violation, right? So we can look at sort of black box methods that are independent of the application semantics itself, so it doesn't really matter what the application is doing. We're simply going to try to run the application in some random way, and we're going to try to see what happens. Now, the problem with this is that not only do we not know anything at all about the application, these black box methods are also agnostic with respect to the particular guarantees that are provided by the underlying database. And there isn't just one, it's not a one-shoe-fits-all kind of thing. Different databases provide different kinds of guarantees, provide different kinds of consistency models. So it's imperative that any black box method somehow understand that in order to be successful, because if it doesn't know what the actual database is offering or what the system behavior is of the underlying database, it's not going to be able to sort of discover interesting anomalies in a meaningful way. And so if you're just going to sort of randomly look at things, you could imagine that this could be time and resource consuming. So we implemented, to figure out exactly how far we can go with this particular problem, as a starting point for our investigation, we took a system, a black box random testing system, based on a well-known distributed system testing framework called Jepsen. And we incorporated that in the context of the particular application domain that we are considering. So we're looking at Java-based database applications. We run on top of a distributed database called Cassandra and a distributed data store called Cassandra. And we wanted to understand how effective is black box testing techniques in discovering invariant violations that occur because of a failure to support serializability. Okay. So we took one particular application to sort of justify the utility of this approach, and that was a well-known OLTP benchmark called TPCC. It doesn't really matter, the details of TPCC aren't really relevant for this particular discussion, but at a high level, it manipulates a warehouse, a collection of warehouses, orders. It's managing a collection of inventory tables and rows, of customers and stocks and so forth and so on. Okay, so what we wanted to do was to understand for 21 invariants that we knew must hold in TPCC, how many of these could we actually discover running random testing using Jepsen in an hour. So we ran for an hour and we tried to figure out how many bugs or how many invariant violations would Jepsen actually discover. And what we found out, green is good for us, bad for the program, right? It means that we actually discovered an invariant violation. So black box testing gets us 2/3 of the way to where we want to be, which is not bad, but it's not great. It means that fully 1/3 of invariants that we know are in fact violated, because we can come up with counterexamples that we can actually trigger, were not able to be discovered within a reasonable amount of time, what we considered a reasonable amount of time, just using a black box technique. So that led us to think if there was, in fact, a mechanism that we could employ that used white box methods, where we could actually analyze, if we could actually analyze programs in a meaningful way, could we actually get all of the red to become green, right? Right, so that's the sort of crux of what we discussed in our paper. So the question is, if I gave you a database program, can you actually analyze it sufficiently? Can you actually generate a symbolic representation of the possible executions that are feasible within this database system to actually trigger invariant violations with respect to some consistency model, right? So the idea here is that we're going to track symbolic dependencies between reads and writes and different kinds of events that happen within databases for an arbitrary number of transactions. And we're going to represent these dependencies symbolically. And we're going to try to trigger we're going to try to trigger serializability violations by essentially trying to construct a cyclic dependency. So the upshot is, a well-known result is that if you have a serializability violation, then those violations manifest as a cyclic dependency between read and write events across different transactions. So if I can discover a cycle in some effective way, then I found a serializability violation. But I have to make sure that these cycles are meaningful. I can't just sort of willy-nilly construct cycles, so I have to make sure that I'm preserving and respecting certain characteristics of the critical characteristics of the system and program semantics. Okay. So the sort of high order bit in this slide is that we simply want to be able to identify dependencies, and we want to be able to track dependencies in meaningful ways. Okay. So in this particular cartoon, in this particular figure, right, we have the same simple program that we talked about before. Observe those dotted arrows. So think of those dotted arrows as an edge between an update and a select that cannot happen, right? Surely the select that's on the right-hand side, on the top right-hand side, is not going to witness the update on the left-hand side, just by the way I've laid out the particular, the two particular programs. But if I follow those edges, and if I follow the dotted and solid lines, I find myself with a cycle, right? I don't have a serial execution here because both transactions are witnessing results that don't include the other, right? We don't have a way of ordering all of the operations in these two different transactions in some serial way while still preserving all of these edges. So the trick is, can I find cycles like this, right? If I can, I found an error, I found an invariant violation, and I can report that and then try to replay it and move towards improving the soundness of my program. Okay. So can we statically construct these kinds of valid execution instances with these kinds of cyclic dependencies? So let me go into a little bit more detail about what the execution model actually is. So we're going to allow transactions to be arbitrarily invoked. So our semantic model is that we're not going to impose any particular restrictions on how transactions can execute, right? We are going to have the operations in transactions can conceptually be executed on any partition in the system. So we have an arbitrary number of partitions which represent all the replicas that we might wish to have. And a particular operation can go to any one partition. And when they do, we're going to establish certain relations. We're going to define an axiomatic characterization of how these operations are witnessed by other operations. So for example, if I have operation 1 which appears on partition 1, and then I subsequently allow operation op prime 1 to also execute on partition 1, well, we believe surely operation op prime 1 gets to witness the effects of operation 1, and so we set up a visibility edge, if you will, a relation between op 1 and op prime 1 that imposes certain constraints, that says no matter what happens, the second operation must witness the effect of the first, right? And so forth and so on. But observe that that op2 prime, which executes on a separate partition, need not necessarily witness or need not necessarily be aware of the other operations on this other partition. That's the nature of the sort of weakly consistent model that we're considering. So things that are sitting in one partition must see each other's effects. Things on other partitions may or may not see the effects of other operations. So like visibility, there are a series of relations that we can define that impose constraints, that impose structure on the execution and the effects that are witnessed by different operations. Okay, so what are some of these other sort of more fine-grained dependency relations that we must consider? So these are all very, very standard if you've sort of done dependency analysis for sequential programs. So we can witness writes. Writes can witness one another. We can witness updates from one write to a read. We can have these anti-dependencies that I said that says that a read does not witness the effect of a write. And we can take all of this stuff and encode it as formulas in a first order logic and hand it off to a theorem prover, right? So we build these large formulas that capture properties of systems. These include, and I'll talk very briefly about what these different structures are. So the first structure is context, which says what constraints must be satisfied by any execution, any valid execution of a program. And these constraints sort of capture classical program dependencies, right? So if I have an update of x to 1, and I have a select, and the select sees that update, then surely the value of x should be 1, right? It should not be 0, right? So that's a write after read dependence. We might have dependencies that relate two updates to the same value, right? So for example, if I have an update of x to 1 and I have an update of x to 2, then surely anybody who sees the update of x to 2 should not see the update of x to 1. Right? We have properties that are associated with the database system itself, the guarantees that are provided by the database system itself. So these consistencies, so there are a number of variants, as you can imagine, on the kinds of guarantees that a database system provides. And we've encoded for a number of databases what those constraints are. And remarkably, we can express all of that using the language of relations that we've developed. And so we have a fairly rich set of invariants that we know that the database is actually going to provide. And we want to be able to make sure that our programs are consistent with what those guarantees are. And then we have other kinds of dependencies, right? We have necessary conditions that must hold between multiple operations. So for example, if I claim that the select doesn't see the update in this particular cartoon, we must have a context in which that's feasible. So for example, it may be that the update is embedded inside of a conditional that demands that A be true, and the select is inside of a conditional that demands that A be false, and these two transactions execute concurrently. And in which case, this anti-dependence makes sense, right? It's clear that both of them can't happen at the same time, and the effect of the update cannot be witnessed to the select, right? So we're allowed to do it. But if we can't establish that kind of constraint, then we can't add that edge. And we have other issues with respect to sufficient conditions. So if we know that the two values, that the two operations on the transaction are embedded inside of a conditional guard that's the same, then we're allowed to establish a visibility edge, which allows us to establish dependence between these updates and selects, right? And finally, we try to find cycles, right? So now we get to sort of figure out, with all of these different constraints, can we establish a cycle? And what we do is we parameterize the structure of the cycle according to three variables: the number of transactions that we get to execute, that are executed serially, the number of transactions that we get to execute concurrently, and the length of the cycle itself, right? So recall, we're not doing verification, we're doing testing. So we're going to bound the anomalies that we're going to discover are going to be with respect to the length of a dependency cycle that we get to establish, right? So if we have a cycle of length k and we can find a cycle of length k, then we know that an execution exists that establishes serializability violation. Okay, so we've proven that this particular structure of the first order logic formula that we've constructed, the symbolic encoding, is enough to address all of these issues that I talked about earlier. We can sort of systematically construct initial database states, we can construct input arguments, and so forth and so on. So we have a system that does this. We've built a system that takes Java programs, encodes Java programs into this kind of symbolic framework, uses Z3 as the underlying solver, and we built a testing framework and a replay framework that does all of this automatically, right? So the amount of work that's required by the programmer is nil. Right, so let me just very quickly conclude with some results that we've got. So we looked at a number of OLTB benchmarks similar to TBCC, and we tried to understand how many dependency violations we could actually discover, how many serializability violations we could discover in 15 minutes. So we bound the time to be 15 minutes, and we tried to discover all cycles of length 4 within that time bound. So In some cases, we were unsuccessful. So TATP, we couldn't find anything. But for a number of other serious applications, seed, small bank, TPCC, we discovered a non-trivial number of errors. So there's promise to this approach. How far we can push it remains to be seen. Interestingly enough, when we look back at the initial TPCC study, we discovered that all of the benchmarks, all of the invariants that we had before were captured. So we were able to discover all the 21 invariant violations using our technique. Our paper's got a whole bunch of other stuff that you can take a look at. And I think I'm at the end of my time, so I'll close with that. Any questions?